Greetings to all. I am Karishma Raut presenting Multimodal Perception for Enhancing Human-Computer Interaction through Real-World Affect Recognition with co-authors Dr. Sujata Kulkarni and Dr. Ashwini Sawant. The outline of the presentation is introduction, methodology, results and discussion, conclusion and references. Affect recognition with artificial intelligence and machine learning techniques has shown tremendous application in assistive robotics, healthcare, and security. The human use different modalities to express their emotions like face, speech, body gestures. The audio and video signals non-intrusively explain how humans express themselves through facial reflections and speech in reaction to occurrence of an emotion. Early studies on affect recognition focused mostly on unimodal methods such as speech and facial expression recognition on lab-controlled databases like extended Cohn-Kanade, more popularly referred as CK plus dataset. These datasets are developed under regulated conditions with maintained reverberation and noise level, typically with minimum speech content, illumination, and calibrated cameras. It is challenging to explore affect information from real-world natural environment, which is full of dynamic situations. The samples are shown in figure for lab-controlled and for natural environment. The unimodal approaches are not sufficient to provide precise information due to change in illumination conditions, head angle changes, occlusions, noisy environment conditions. Real-world emotion recognition can be benefited by multimodal learning that uses the complementary data of various modalities to increase comprehension of emotions. The most popular non-invasive mode that can provide rich contextual information is audiovisual data. A comprehensive literature review highlights the need to explore pre-processing real-world data, as it presents different conditions compared to lab-controlled data. This stage is crucial for effective feature extraction within the framework. Many researchers have worked on combination on different features and feature extraction fusion techniques to improve affect recognition. It was highlighted that cross-corpus evaluation, which means use of multiple databases for evaluation, is required to develop precise models that can sustain in different environments. Hence, the paper contributes as follows. The difficulties in pre-processing real-world data are emphasized through experimental evaluations and comparative studies using various detectors on uncontrolled and real-world visual data. The influence of this pre-processing on feature extraction and key feature selection is examined by analyzing the outcomes from a pre-trained CNN model applied to CK+, RAF, and a few datasets. The relative importance of another modality is highlighted through multimodal comparative analysis in real-world scenarios. The methodology describes real-world audiovisual affect recognition framework, pre-processing challenges, unimodal approach for visual, and cross-corpus evaluation on multiple datasets. Finally, multimodal approach for real-world data. Generally, audio-visual emotion recognition approach consists of 4 steps: audio-video extraction, pre-processing, and face detection and alignment, and voice and unvoiced region detection, feature extraction from various modalities, and finally, fusion in multiple ways for classification. The realistic dataset of AFEW, SEVA, and RAF can be used. The database contains videos showing natural head poses and movements close to real-world illumination. The AFEW and RAF datasets is containing more relevant and balanced data and selected for cross-corpus evaluation. The various pre-processing techniques for face detection and alignment are OpenCV, single shot multi-box detector, multicascade convolutional neural network, MTCNN, and retina face. Visual features can be extracted based on appearance, based on geometry, based on dynamic texture based, and the most uh, relevant is deep features extracted from deep models. Audio features can be extracted like prosodic features, for example, zero crossing rate, spectral features like male frequency spectral coefficient, spectrogram, cochleogram, modulation spectral feature. Various fusion techniques like feature level fusion, decision level fusion, or intermediate fusion, which is a data fusion at different stages of model training, can be used. The multimodal framework shown in figure comprises of visual data classification with deep CNN using facial emotion recognizer pre-trained model and audio data classification using CNN model trained by basic audio features. The results obtained from visual modality and audio modality can be analyzed separately to observe contribution of each and can be fused together for enhancing effect recognition. The initial stage involves identifying and positioning the face since it has the most noticeable visual cues. The application of deep transfer learning through a suitable face alignment technique closely resembles the pre-trained deep neural networks training environment for emotion recognition. The fact that there are more data available to train recognition model is one factor in this decision. Augmenting facial details for fine-grained classification is the fundamental idea behind both problems. An open source Python package called Face Emotion Recognizer makes use of convolutional neural network that was trained using the FUR 2013 dataset. It provides rich features while training deep neural network with another dataset by overcoming scarcity of data. The 2D convolutional neural network is inspired from VGG face network. It consists of 5 convolutional layers and each layer followed by max pooling layer. This layer is finally connected to fully connected layer followed by softmax function for classification. The audio classification is a 1D CNN model consisting of 3 convolutional layers and each layer followed by a max pooling layer. The key auditory characteristics for identifying emotions includes pitch, spectral energy distribution, male frequency spectral coefficient, and zero crossing rate. This is given to 1D CNN model. The final layer of 1D CNN model is fully connected layer which is followed by softmax function for classification. The weighted score level fusion is used for final classification with equal weights assigned for both the modalities. Only accuracy cannot be a measure of evaluation when data is unevenly distributed. Hence, appropriate evaluation is carried out using precision, recall, and F1 score. The impact of real-world diverse conditions is analyzed using different pre-processing techniques on visual data. The deep face Python framework with VGG face model is used to detect and align face from real-world dataset. The framework supports different face detection techniques under one roof. The complex head position and illumination have a severe impact on the performance of OpenCV, SSD, and DLIP detectors. These detectors are not able to detect the face in dynamic conditions. Frontal faces are detected by all detectors. The face is detected by all but not properly aligned by OpenCV and SSD. MTCNN and retina face detectors are only successful on head pose variation and illumination effects, whereas MTCNS is providing more aligned key face areas. The 5% data from a few dataset and 2% data from RAF dataset containing extreme head rotation and illumination are not detected by any detector. These pre-processing issues are one of the major reasons for the poor recognition rate in real-world conditions. This can be analyzed by comparing the recognition rate of lab control dataset and a real-world dataset for a particular framework. Hence, comparative analysis of unimodal approach for affect recognition is carried out in lab-controlled and natural environment. The pre-processing results from experiment 1 suggest use of cascaded empty CNN network to sustain in real-world dynamic conditions. The visual data for affect recognition using deep convolutional neural network with pre-trained CNN model is analyzed using lab-controlled dataset CK+, and a representative wild dataset RAF and AFEW. The obtained accuracy for CK plus is 62.58% due to its frontal face location. The 5% data from a few dataset model was not detected by model, and for rest it has 31.07% average recognition rate. The average recognition rate is observed for emotions happy, neutral and sad. The fear and surprise are poorly recognized and disgust is completely misclassified. Around 2% data from RAF was not recognized, and poor recognition rate can be observed for disgust and fear. The average recognition rate in terms of true positives for RAF is 52.02%. A facial expression may occasionally be confused with other expression in the wild when numerous expressions coexist together. The extreme illumination conditions, head positions, and occlusions are responsible for not detecting few data from dynamic dataset AFEW and RAF. These are some samples from data which are not detected at all. A comparative analysis of unimodal and multimodal approaches is conducted in natural environment. The datasets used for training model is AFEW with 774 videos, and test dataset is containing 383 videos from AFEW datasets. The figure shows sensitivity analysis of unimodal and multimodal approaches for emotion classes. The visual modality is providing 31.07% accuracy. Audio modality is providing 33% overall accuracy, whereas multimodal approach containing audio-visual modality provides 34.98% accuracy. Each modality is good at recognizing few emotions. However, combinedly, all emotions can be efficiently recognized. It is observed that audio modality is excellent performance in recognizing anger, whereas visual modality is good at recognizing happy. The fear is recognized in better way when both modalities are present. The performance of surprise and disgust can be improved using more detailed features. As mentioned earlier, dataset contains less information about surprise and disgust, and hence model is not trained in balanced way. The data augmentation can be applied to emotional data having less information. Also, different fusion techniques can be explored to enhance the affect recognition rate. The takeaway from above discussion is the unimodal analysis is essential to understand contribution of each modality as well as problems encountered by the modality. Each modality is good at recognizing few emotions. However, combinedly all emotions can be efficiently recognized. The impact analysis of pre-processing is guiding for feature extraction and requirement of additional modality. The way data augmentation applied to enhance information can be changed and more weightage can be provided to classes with less data. The real-world situation present greater difficulties for face detection and alignment as compared to controlled situations. So we can conclude from above discussion that due to occlusions and non-frontal head postures, the original face expression could appear differently. It has severe impact on the misclassification of different emotions, specifically anger, fear, surprise, and disgust. The unimodal approach showed 31.07% average recognition rate for real-world dynamic AFEW data, 52.02% for RAF line data, and 62.58% for frontal CK plus data, which is a limited environment data set. Moreover, 2 to 5% data from natural settings went undetected, prompting the inclusion of an additional modality. By incorporating audio modality, emotion recognition in the real-world context is enhanced, providing both relevant and supplementary information. It showed improvement in overall recognition of natural emotions. It also highlights that data must be analyzed in coarse to fine manner to appropriately recognize key areas that are responsible to give prominent features. Future performance can be boosted by exploring deep learning models to capture dynamic and detailed features from videos and by investigating various feature fusion techniques. These are the references. Thank you.